computer. Okay.
Recording in progress.
I'm hearing myself. Okay, all right. So I think last week we were looking at the fact that sometimes you have structures that do not have static loads, all right, or do not have stationary loads, but we have loads that tend to move with respect to time, all right. And one of those structures can be a bridge, right? A vehicular bridge where vehicles tend to go across. And these bridges are structural elements which are designed to help move the vehicles from one end to the other end. And bridges come in different forms, right? So typically we have the basic concepts which we call the corvette, sorry, where it's most likely there's a drain, and then we have some bit of concrete over that drain, and then vehicles are able to pass over. And then we have the most elaborate bridges out there, some being the cable stayed bridge, some being the suspension bridges. Example, and I think the San Francisco Golden Gate Bridge, and I think that's a suspension bridge. And then I think the something aqueducts in Paris, France. So we have many examples of bridges, right? They are different categories of complexities. Okay. So what this means is that, but they perform the same function, right? The goal is that transport a moving load from one end to the other. Okay. So because we do have moving loads, what this also implies is that finding components like shear force and bending moment diagram for the entire structure. Let's say if it's a beam, for the entire beam becomes very complex, or I would say almost impossible to do, because then you need to find the shear force for the entire beam at every instant in time that the load moves, right? So if you have a 10-meter bridge, for example, I want to find the shear force. So let me come here. Just give me a second. So let's say if you have let's gonna do some recap. Yeah. So basically, if this is your bridge, all right, and you have on it a moving load, right? So this load, let's say it's a car, so it moves maybe 20 kilonewtons, right? It moves, which means that at every instant in time, if you want to find a shear force for this beam, you have to draw a zillion of these shear forces, right? Because if let's say at every second, for example, so at every second this car moves. So at every second you need to come back, find your reactions, and draw shear force diagram, right? So if it's going to take the car about maybe maybe assuming it's 10 meters, and every second it covers even 1 millimeter, or maybe let's say maybe 10 centimeters or some number like that, that means that you're going to have to do these calculations for over about 10 times. This is like in its simplest form. But the longer the span, the more drawings you have to do. All right. So we came up with this concept. All right. Instead of finding, so that instead of finding shear force, bending moment, or and even reactions, right? Okay, some even different. Okay, can we look at deflections? But instead of bending moment shear force reactions for the entire beam or the entire span at every instant in time or at every point in time, we don't want to do this, okay? So rather, what do? We rather look at the effects of the moving load the effect of the moving load at a point on the beam. Okay, so come back to the structure, we pick a point on the structure. Let's call that point C. All right. And as the load moves from A to B, what would be its effect on point C? Assuming we want to find shear force. So we find shear force at C. We find bending moment at C. So the load moves from A to B. When the load is at A, what is the bending moment at C? When the load moves to some distance away from A, what is the bending moment at C? So at every point, we are looking at the effect on C, all right? It can be C, it can be B, it can be A, it can be K. It can be any point, but we always pick a point at a time. And then whatever diagram we are drawing becomes the influence line diagram, all right? So it could be the ILD for bending, ILD for shear, ILD for deflections, ILD for reactions, okay? And that's what we've been doing, okay? Um, so a few things to note. One, we do not know, or we do not have, we do not know the distance, maybe, or the position. We do not know the position, or let me put it this way, rather. Uh, the position of the load varies. I think that's a better, right? The position of the load varies. So what do? We represent that position by X, all right? And then we find all our relevant information based on X, okay? So once we get all this relevant data or values based on X, then now we can say, okay, if X is 0, if X is 1, so we can now put in different intervals of X and I use that information to determine whatever diagram we are looking at, okay? So that if, so here, let me just, so we can call this distance here from A to where the load is at this point in time, X, because that X varies from between A, so X will vary from between L and then 0, between A and B. All right. So that's what you guys did in first year, first semester with the basic structures. And we are building on that, right? We are no longer looking at statically determinate beams, but now we are looking at statically determinate trusses, right? And I did explain that when it comes to trusses or pin jointed frames, that's right. Basically, we are looking at a perfect frame, not a deficient or a redundant frame. Okay, I'm guessing we know what all these things are. So this is a typical example of a frame. All right. And there are two options, depending on how the structure is designed. You could have two cases where the load is traveling. All right. So the position of the load varies. That is one. Two, Oops, what is happening to the pen? That doesn't want to change. Okay, okay. All right. So to locate um, on which chord the load is traveling. Okay. Or the load is moving on. Okay. So we have something that's interfering with my screen. Please, if you're sending chats, Edward, can you hear me now? Is he the only one who cannot
Yeah,
hear me?
yeah, I can hear you now.
Okay, okay, great, great. All right. So let me reset something. I don't know. I think my uh yeah, I'll just reshare shortly. I don't know what is happening from my end. Trying to close a bunch of things that might be interfering with my um software or program. Um, so let me retry. Hopefully it works. Um, share the screen again, and then this time around, let's hope everything works. Sometimes, yeah. So locate on which chord the load is moving on. Very important. Okay. So you can have the bottom chord, okay, and also have the top chord. Okay. So please, the question usually, I mean, in exam, the question usually will specify which chord the vehicle or the load is moving on, but just so that you always look out for it, because it's important to know which chord the load is moving on. If you choose a wrong chord for the load to move on, your calculations obviously will not be correct. Okay. Then obviously also, I mean, as you're looking for the chord on which the load is moving on, also pay attention to the positions of the supports, right? Supports could be top and down, it could be left and right, it could be anywhere. So always take note of the position, because sometimes students are fond of the fact that, okay, maybe they've solved a few questions with bottom chord moving load. So the brain picks up that information as that every structure therein or every truss therein has only bottom chord moving loads, which is not the case. All right. Okay, so once we have that in play, and then we locate which load we are on, now the third one will be to determine which members um, the ILD is needed for. All right. In real life or in real life design, you will do for every member. All right. Then you look for the most critical member. But in exams or in classwork, we we draw the ILD for just a few members, maybe 3 members at most. But in a design office where you're designing influence line diagrams for um, reactions or maybe for forces in the axial members, what happens is that you will do for all of them. Okay. Then from there you can decide on which one has the worst effects and then design accordingly. Right. So here, maybe if I'm looking at these two, maybe this, oops, wrong color. Let's have a look at this chord, that chord, and that chord. So, I mean, this members always identify the members you are working with. It's important. Always, always. Maybe it could be this three on the left or this three on the right. Whatever be the case, always identify the um, the members you want to calculate for. Someone's phone is on or someone's connection is, his mic is on, all right? So let's put our mics off just in case we don't reveal secrets, all right? Okay. So determine which members the ILD is needed for. So once we find that, then on that, you can use so you can use either the method of sections or the method of joints. Okay, it's up to you. But because we are looking at only a few members, then their method of joints becomes important. I mean, or the most useful tool to go for. So I would advise that if you are, for some reason, forgotten some of these things, please go back and revise your lecture notes on that. All right. Um, so once we choose one of these methods, then the next point would be that we try to determine the ordinates. So that's the y-axis, I believe. Ordinates is y, abscissa is the x-axis. Yeah. Determine the ordinates for the members or the ordinates of the ILD, right? So for the members for different positions of, so the movie load, all right. But here we use a 1 kilonewton movie load. All right, so we don't use that. So even if the actual load is 20 kilonewtons, all right, we'll prefer to use a unit load, draw the influence line diagram based on that unit load. Then from there, use that information and then the 20 kilonewton load and determine certain important values like the reactions, like the shear, like the bending moment. Okay. And when you're dealing with trusses, it is easier to use the side without the 1 kilonewton load. All right. It's because mostly we would prefer to use the method of sections. All right, which will require us to divide our truss into two parts, right? So we have the left-hand side and the right-hand side. All right. So the load is moving from one point to the other, the 1 kilonewton, or the let me say the unit load is moving from one side to the other. And what that means is at some point it will be on the left of the section you cut, or let's say if you cut a section, maybe cut a section through. So this is your X, this is your KK. You cut a section through the truss. So you have the left-hand side, you have the right-hand side, all right? So that if your load is moving at some point, the load is found on the left-hand side, and at another instant in time, this moving load has now moved to somewhere on the right-hand side. All right. So what I'm saying is that if the load is on the left-hand side, like in this case, it is easier working with the right-hand side portion to find the forces in the members. Now, when the load moves to the right-hand side, so now your load is now somewhere here. If the load moves to the right-hand side, then it's easier working with the left-hand side. And it's easier, right? It doesn't mean you cannot work with the opposite side, but usually you work with a side that does not have the moving load. All right. So that's what I mean by that. It makes for an easy calculation. All right. That's the plan. Uh, that's my mouse. Yeah. So that's like basically what I tried to do the last time that we met. So I'm going to bring up an example, solve it with that same idea, and then we'll see what we mean by that. Okay, so maybe this will be a little bit slightly complex compared to what we had last week, but the same format, the same everything. Nothing really changes. Okay, so let's look at an example. So let's say I have this pretty much. Okay, let me draw it nicely. Sometimes you want to look good. So we have this structure, hopefully. Anyways, if it looks bad, that's fine. If it looks good too, we'll be very happy. Why am I even worrying myself? Okay, let me. All right, it's fine. Let me just go ahead and keep drawing. Let's see how this thing looks like in the end. Okay, it's not looking like the way I want it to look like. So let me just do the freehand. All right, at least I have this guy, so it's fine. I don't want to spend forever drawing this. Am I missing? Hopefully I got everything. Let me label them. This is A, B, C, D, E. How many do I need? One, two, one, two. I'm missing something. Oh, okay. So there's something here. All right. So that's what I'm missing. Okay. So B, C, D, E, F, and then G. Okay. So we have something like this. Yeah, it looks funny, but let's work with the funny bits. All right. So A, B, C, D, E, F, G, H, I, where's my J, K, and L. Great. Um, okay. So my supports are at A, and then support at E. So I'll rewrite the E again. So I have my support at A. Why clean everything? Okay. So my supports at A and then E. All right. So this is A and this is E. All right. So the dimensions, very important. So this is, let's say, six. There are six spans, and each one is 3 meters. All right. And then my height is 4 meters. All right. And I'm to draw. So the question states, stay in one place. All right. So I'm to draw the ILD for members. Let's remember CI, member CD, member DI, member IJ. So there's like a tall list, right? Member FL, and then member HG. I won't do all, I'll just do a few, right? So that we just see what goes into it. So if you have all of that, okay, what else do we need? So, and this will state that the load moves or travels on the bottom chord. Okay. So let's look at the members that we are supposed to design, or in this case, find the forces for. So I have CI, so this is my CI right here. I have my CD, I have my DI. So these three, they make a set. And I have my IJ, where's IJ? So any of these three should make a set. IJ, FL. This is my FL right here. Then I have which one again? HG. I can't have HG. I can have HI, not HG. Sorry. So let me correct this. This is HI. So this is my HI. All right. So I'm looking at this 6 members. All right. This will still require you to use method of sections. All right. So one section that we can look at would be, we can cut a section through this right here. So let's call this section XX. So this will pass, so XX will pass through IJ, pass through DI, and pass through CD, which is great. If you cut your beam or your truss into sections, and the sections are more than 3, you will not be able to solve them, at least with the law of statics in terms of being statically determinate. All right. One other way we can also cut this is to cut it through something like this. So I can call this ZZ. Okay. So if we cut through ZZ, we'll have what? HI, we'll have CI, then we also have CD. All right. So we can use that. And then for FL, we can use method of joints for FL. So these are like some of the ways by which we can solve this problem. I'm not saying this is the only way, but at least so far, this seems to be the easier way. All right. So I'm going to go with, so I have the FCI, FCD, and then, so I just do two. I don't have to do, so I'll look at, let me just highlight the ones I'm going to. So I'm going to look at FCI. look at FCD, and maybe if you have time, look at HI, right? You can look at any of them, okay? So maybe as something for you to try out, you can complete and then send the information to me, we can discuss, all right? Okay, so great, let's find the support reactions. Let's find VA, let's find VE. Okay, let me just bring this so that I don't have to end up creating a mess. Let me just copy that, put it here, and then do some bit of deletion. Don't need you. So since I'm dealing with CI, it means that I will be focusing. I don't need. Let me just delete this guy. Will it go? Not going. Okay, it went, but it went with the beam as well. Okay, let's go back. Let's take you. Okay, it's easier cleaning things like that. Okay, I'll just redraw this guy, so it's fine. Now let's bring you back. Um, I should have first done the copy when okay, so we have, so I'm looking at CD and then CI and then FL. Let's say FL. I think I chose HI rather, not FL. Ah, it's fine. All right. Whichever one I want to work with, HI also is fine. All right. So here I want to find the reactions VA and then VE. So we have our load moving in the bottom chord. So let's say that our load is now at point B, right? Like we are just assuming that the load is now moving to point B and it has covered a distance of X. All right. So what do? We cut a section XX. That'll be a bit confusing. So let me call this one section X1. Just say X1, X1, so that at least it doesn't create the impression that we are using the same X. It's just separation, right? So we would know that it means that VA plus VE will be 1 kilonewton, all right? Because our unit load is 1 kilonewton. I can take this guy away. I don't need a 6. It's already up there. So you have a 1 kilonewton load at B, right? I mean, we know B, the distance from A to B to be 3 meters. But here, because it's a moving load, we represent its distance in time as X. All right. So that if you take moment, summation of moment about A to be equal to 0, then it's VE times 18. All right. Am I no times 12, sorry. So from E to A, that distance here, 1, 2, 3, 4. 4 times 3 is 12. The entire length of the bottom chord is 18 meters. The distance between A and E is 12 meters. All right, so it becomes V times 12 will be equal to 1 times X, or let's say minus 1 times X equals 0. It's the same thing. So that our VE is equal to X over 12. All right, which means that our VA will be equal to 1 minus X over 12. So these are your reactions. They will not change, or they will change because X will vary. But in terms of X, they will remain as this, as X moves from what's the name? Um, A to E. All right. So for example, um, so I can draw a table on the side, I think. Let me draw a table on the side. It's going to be one funny table, but let me just draw a table on the side. See what happens. Just play around and see what happens. So, okay, let me just use this guy to draw the table. Hopefully I don't overdraw. I'm gonna need more lines. So I'll stop when I need to. All right, so I think this is fine. So I have other space. Okay, so this is the so the member is right here. Yeah. So I have member. Oh, no, okay. So the member, sorry, let me do the joints. Sometimes okay, so let's do the joints rather. Let's look at so I mean where x if x is 0, so x, so let's use what am I doing? I'm gonna do sorry. So let's look at joint A, B, C, D, E, F, and G. Okay, so I don't need to go all the way down here. Thankfully, it makes my work easier for me. Okay, so I need to get rid of everything else. Great. Okay. So here, the value of x when a x is 0, so x is 0 over here. At b, x is 3, then 6. Sorry, 9. At e is 12. At f is 15, and at g is what? 18. Okay, so now let's look at v and v. Let's play with it. Okay. Oh, I should have deleted more of those guys. Okay, it's fine. So let's look at so VA will be what, right? So we have an equation for VA. We also have an equation for VE. So just take these equations as we see them and then put in the value of X. All right. So for example, so if X is let's say if X is equal to 0, VE will be 0 and VA will be 1, right? If X is equal to 3, so that is at B. So at BX is equal to 3, then VA will be 8 over 12. Am I correct? No, 9 over 12, sorry. And then VE will be 3 over 12. Okay. All right. And 3 over 12 is the same as 1 over 4. Okay. So I can come here. This is 1. This is 0. At B, this is 3 over 4. This is 1 over 4. Okay. At 6 meters, this will be half. This will be half. At 9 meters, this becomes 1 over 4. This is 3 over 4. At 12 meters, VA is 0, V is 1. Okay. Now let's see at F, sorry. So at F, which is when X is equal to 15 meters. So we are somewhere, we are here. Right. So now the load has moved to F. If the load is at F, what happens? So just put it in there. What will you get? All right. So it means that our VE will be equal to what? X is, so it becomes 15 over 12. And 15 over 12 is the same as what? 5 over 4. Great. So our VA, which is 1 minus X over 12, becomes 1 minus 15 over 12. And 15 over 12, 1 minus 15 over 12 is the same as what? Minus 3 over 12, the same as minus 1 over 4. All right. So whilst at F, VE is 5 over 4, VA is minus 1 over 4. Okay. If you do for G, VE becomes 3 over 2, and then VA becomes minus 1 over 2. So just slotting in the values of X for these two equations. All right. So that's our VAV. Simple. So we found that. So if the question says draw the influence line diagram, sorry, for reactions at A, then you can use the information over here and draw for that. Okay. So let's just draw it. I mean, let's just draw it for the fun of it. Okay. So let's draw the ILD diagram. If you have, please, if you have any questions, you can always unmute your mic. You can text or whatever. But text to the other Lawrence and Ladi without the hosts so that I can see. If you text to the hosts, I have to always pause and check and pause and check. All right. So please take notes. All right. Great. So the ILD diagram for reaction at A. Okay. So again, okay, so I have this structure. Let me just draw the base or the abscissa. So just locate the various points A, B, C, D, E, F, and G. Right, just locate them. Or you can use 0, 3, 6, whatever. Okay. So at A, we had 1. All right, then it came to 3 over 4. It came to half. Then it came to 1 over 4, and at E it goes to 0. Then at F it becomes minus 1 over 4. Then at G it becomes half again, right? So typically, this is how, yeah, it's supposed to be a straight line. I know it doesn't look anywhere close to what I'm supposed to be having, but that's fine. I'll just do the corrections. Um, so your ILD diagram will look like this. Don't worry about the points. The points, I know they are a bit off, so I should be able to correct them. Let me put a point here, put a point here, put this point here, put this point there. Yeah. So, and it's best practice to write the values as well. Please take note. So the values here will be half, 1 over 4. Here will be 1 over 4, half, 3 over 4, and 1. This is positive, and this is negative. All right. So we can draw something similar also for the reaction at for VE. It's to take the same form, but then your diagram will be different. Okay. So again, I have the answers over here. Try that on your own and let me know what you get. Okay. So now let's move to the yeah. I did some update to the PC and I'm sure things are looking funny, but it's fine. Okay. So let's cut section X, X1, X1, as I call it, or section XX. Interestingly. And let's see how let's see how simple it is to go about this approach. Okay. So I think I can take this information here now and then come again and place it in the space. So I'm going to cut a section x1. I didn't copy that. X1 is fine. So let's do something interesting. It's always easier to do the lazy man approach. Okay, so I can copy the one here, move it slightly towards the left. Great. Okay, this is what I'm looking for. It works. So just let me just make sure that oops, I don't need this guy over here. So let me move you back up. Okay. So do the same for the 1, 2 here. Take this guy out and bring you back. Okay. So I have two sides, right? So this is the left-hand side, and here we have the right-hand side. Okay. So initially, the load is going to be found, the unit load is going to be found between the also it's going to be found between the or it's going to be found on the left-hand side. Okay. So if let's go with an if statement. So if the unit load is on the left-hand side, use the right-hand side for the calculations. Okay, so that's what I've been meaning to say, but that's what I've been trying to get you guys to look at all this while. Okay, so in this case, our load is somewhere between A and C. So on the left hand side means that our load. This my S looks funny. Okay, so here our load is between so it's between A and then C. All right. So we need to find these forces. Okay, so let me call this one FIJ. This is FDI. This is FCD. And it's going to be the same in opposite directions. One of the rules of Truss's calculations, we assume that the forces in the members are in tension, so they're moving away from the joints. All right. Then when you find your answer and your answer is negative, it simply implies that the forces should be compression. All right, but that's what we do. So this is FIJ, FDI, and FCD. I haven't done anything, just rewriting my information. Did I cut the right place or the wrong place? Let me see. Let me go back to my section and see which one did I cut. Oh, I actually did the ZZ run instead of the. Okay, so let me just go back. I don't want to go. It's fine. It means that I'm solving a different question now, which is fine. So I'm finding FCD, FDI, and FIJ. It's fine. So let's go ahead and solve it. So I don't have to confuse you guys with changing stuff. So so here I'm using the right hand side. Okay, so I'm going to take the right hand side as we stay away. I'm going to take the right hand side, copy that and place it over here. Okay, so it's what we have seen so far. I haven't, yeah. So here we know that our V is what? X over 12 with already found what V is. V is x over 12. So now this is what we have to work with. All right. We can find the angle here. These angles, we can find them easily. This is theta. We can find theta to be the same over here as theta. So let's go ahead and find theta. Okay, so just on the side here, we can find theta. So if this is what I have, the box will be too small. If this is what I have for theta, okay. So this is 3, here is 4, this is theta. It makes this one 5. All right. So sine theta is 4 over 5. Cos theta is 3 over 5. Tan theta is 4 over 3. One, Mustafa, for adjustment. So these are the angles for this points. So let's go down here. So we know what our theta is, so it's fine. So this is theta, in case we are looking for. So this is theta. Now let's sum vertical forces. All right, it's easier that way. The summation of vertical forces equals 0. So here is VE plus the vertical component of FDI. So plus FDI sine theta equals 0. Please, they are all moving in the same direction. Take a note of it. So it means that our FDI will be equal to VE over sine theta. So this is equal to our V is x over 12. So let's say, let me make it, so x over 12 divided by sine theta was what? 4 over 5. So 4 over 5. So let's write this one properly. This is going to be x over 12 times what? 5 over 4. So it becomes, we can do the math. So it becomes 5x over 12 for 48, I believe, right? Is that what we are all getting? So this is your FDI. Sorry, there's a negative in front of it. All right. So please take a note. So it becomes negative. So our FDI is negative 5x over 48. So, and this is when the load is between 0 and 6, right? When it's from 0 and 6. Okay. Now let's find the other ones too. So let's take moment about D. It's easier that way. So taking moment about D to be equal to 0, we end up with VE times 3. From E to D is 3. And about this will cause a counterclockwise rotation. And it will be in the same direction as the Fij. It's going to be Fij times 4. Okay, so this height here is 4 meters. All right. So both Fij and Ve, their moments are in the same direction. Please take note. In the same direction. So all of this is going to be 0. So it means that our Fij is equal to minus 3Ve over 4. Okay. And this is going to be minus 3 over 4 times x over 12. So this will give us minus x over 16. All right, 3 over 4 times 1 over 12 is 16. So this becomes your Fij. So once you find Fij, we can easily find FCD. All right. So I thought I was going to do which ones? I was going to do, so I ended up doing, so I wanted to do C, so I'm going to do CI initially, but I think I changed it. So let me just highlight the ones I'm doing now so that I don't create too much confusion. Okay. So now I'm doing CD, which is fine. I'm doing IJ and I'm doing DI. All right. Then later you guys can deal with the rest. So it's great.
Hello, sir.
Yeah, hello.
Yes, sir, please, can you take your time? We are analyzing the reactions, the calculations for the reactions.
It's a lecture. So once it's a lecture, well, anyways, okay, so go ahead and analyze the
Yes,
reactions. All right.
thank you.
So let me take you back to where I had my reaction calculations, and this is the reaction calculations. Okay. So let me know when you're done with the analysis. Okay.
No, just something we are done. Sir, this one we are okay. Sir, the section part, sir.
Oh, so here. Okay.
First, yes, sir.
So the right hand side. Okay.
Yes.
So the main thing is that when the load is on the left hand side, it's easier using the right hand side for your calculations. Okay. That is the key thing that we should always focus on. Okay. So let me take you through it again. Okay. So here in this space here, I'm summing vertical forces, right? You can see VE, that is one, FIJ, FDI, and FCD. If you add them all up, these are four forces, including the vertical reaction at E. All right. FIJ is horizontal. FCD is also horizontal. FDI is inclined, which means that FDI has both a horizontal and a vertical component. All right. VE is strictly vertical. So I looked at the vertical component of FDI, which will be going upwards. So both FDI vertical component and VE are all moving upwards. So they are in the same direction. All right. So that's the reason I have here VE plus FDI sine theta. I always prefer to have my theta um, adjacent to the horizontal. It makes things easier. Why? Because back in your SHS and your GHS, mostly anytime you see theta, it is subtended to the horizontal line. All right. So that vertical is sine, horizontal is cos. That's how your minds have been conditioned to work with. So if you put your theta in the different position, it could mess up that kind of conditioning, right? So again, to work with that thinking process, it's best to put your theta whereby the inclined line and then the horizontal line makes that angle theta. Okay. So we count VE plus FDI sine theta equals 0, summing vertical forces. And here I make FDI the subject. Okay. So FDI, sorry, there should be a negative over here. Okay. So FDI will be minus V over sine theta. All right. F V is x over 12. We've done that already. And then sine theta is 4 over 5 from what I wrote earlier. So if you put this in even into your calculator, you should get minus 5x over 48. All right. And this x here is valid only when your load is between or is from A to C. All right, not D to G. When your load is on the other B, the other truss. Okay. Now we want to find, so now we know our FDI. We need to find FIJ or we need to find FCD. All right, one of them. So it's easier to find FIJ first. I mean, it's up to us. We can do whatever we want to do. So here we take moment about D. Okay. So we take moment about D right here. And if you take moment about D, you eliminate FDI and FCD because FDI and FCD are passing through the point D. So the moment due to these forces would be 0. So in that case, you only have moment due to VE and moment due to FIG. Okay. So if D is your point of interest or your pivot, then the the perpendicular distance between point E and D is 3 meters. So it becomes VE times 3, which is an anti-clockwise rotation. All right. Then if you look at FIG is also trying to pull the truss also in an anti-clockwise rotation. All right. So they both have the same direction. So they both can be positive or they both can be negative. It's entirely up to you. So since FIG is horizontal, its distance to D will be what? The vertical distance 4 meters. So it becomes FIG times 4, and all of this is equal to 0. All right. So here we make FIG the subject. So it becomes minus 3 VE over 4 being equal to minus x over 16, since VE is x over 12. All right. So now we know our FIG, we know our FDI, we need to find FCD. Okay. So to find FCD, we have 2 options. Let me exaggerate. So we know that, so this point here, this will be our point I, right? I'm drawing this because it's not part of the structure, so I'm just using short dashed lines to show you guys that, okay, this forces would meet at a point, right? Forces are what? Vector entities. They have direction, so they tend to move. I mean, you can follow the line of action of these forces. All right. So you can either take moment about I, and then by so doing, it's easier to find FCD, or you can use summation of horizontal forces. It's up to us. Okay. So let's look at the easier one, which I think is the summation of horizontal forces equals to 0. So it's FIJ is moving towards the left. That is fine. Plus FCD also moving towards the left. So it's fine. Plus the horizontal component of FDI also moving towards the left. So they are all in the same direction. So here, my FCD is equal to negative FIJ, minus FDI cos theta. Okay. So what is so this is minus FIJ is what? Minus x. So it becomes minus x over 16. Then minus into bracket minus 5x over 48. Cos theta is what? I think it was 3 over 5. Okay. So this becomes x over 16. This becomes, now let's look at this this calculation. I always say it's easier with a calculator by your side. So this will give me plus x over 16. Okay, so this becomes 2x over 16, and now be x over 8. All right, you can always check this and see. So we have these 3 actually. So minus 5x over 48, and then minus x over 16, and then x over 8. Okay. So maybe I can bring this table that I drew earlier all the way up here. I can bring that table down, since I will need to complete the table. So to make things easy, bring you here. Okay, so I'm bringing this table down right here. Okay. So I need to draw one more line. So let me just make a copy of one line. Oops, it's not working. Copy. paste. Okay, let me just put you here. Great. Okay. So here, let me call this, maybe let's do this one, FDI. Says FIJ and then FCD. Okay. So again, these equations are valid for when x is between 0 and 6. Please take notes. All right. So these three equations here, these three equations here would only work for just these three portions. Okay. Please take note. So if x is 0, all of them are 0. If x is 3, then it means that here we'll get for Fij, sorry, for FC, let me just put this FCD, sorry. So for FCD, we get 3/8. I should, yeah, I'm correct, 3/8. Then for Fij is minus 3/16. Then for FDI it becomes minus 5/16. All right. Okay. Then at 6 meters, yeah, we get what 6/8, and 6/8 is the same as 3/4. So 3/4. Here we get 6/16, which will give us, again, here will be minus 3/8. And then here we get minus 5/8. All right. So we are done with the left side using the right hand side. Okay. Now, so now if don't do it again. Okay, I don't know what's happening. Sometimes I think updating the OS is messing things up. So if the load is on the right hand side, use the left hand side for your calculations. All right, that's or to find the forces in the members. All right, that's basically what we are looking at. So it means that here, when your load has moved to, I'm not able to change the color of my pen. I don't know why again. So if the load is between 6 and then 6 and what 18, right? Oops, and 18. So that's between C and G. All right, in between C and G, then we use our left hand side for the calculations. Right, take note. But the X values are for the right hand side. This thing is okay. My mouse is simming. Okay, let's see what's happened to the screen. Never update your OS. Just give me a second again. I don't know. I think I have to refer to my Windows 10. I changed to Windows 11 and I'm having issues. Okay, so we are back. Hopefully we are back and we are live. Okay, so I'm just going to copy this one here. All right. So let's bring it down here. So here, because the load is on the right-hand side, I wouldn't see this, right? So the load is on the right-hand side. So I have this equation here.
Hello, sir.
VA. Yeah, sorry, come again.
That means we can't see your screen.
Oh, you cannot see my screen. Thank you, thank you. Oh, okay. So I was showing without sharing. Okay, interesting. Where's my share? Okay. Hopefully now you can see my screen. Yeah, you can see my screen. Okay, good. So the load is on the right-hand side, right? So if I'm looking at the left-hand side, I won't see the load over there. So VA is what? 1 minus X over 12. Okay. So now let's find FIJ, FDI, and FCD all over, like what we did for the previous calculations, okay? So here's our angle theta, at least that we have already established. So let's say summation of vertical forces equals 0. So we have VA, which is moving upwards, minus the vertical component of FDI. Because that one is going downwards, so you get this. All right. So our FDI is equal to VA over sine theta. So it becomes 1 minus X over 12 times 5 over 4. So this becomes your equation. You can leave it as it is, or you can expand it if you want. It's entirely up to you. This way, to me, is the best. Then let's also take moment. Let's say summation of moment at I to be equal to 0. So we get VA times 6 meters. VA will cause a clockwise rotation about I. Okay. Then FCD will cause an anti-clockwise rotation about I. Okay, so then the length is 4. So this is 0. So our FCD is equal to 4 over 6. Sorry, what am I doing? 6 VA over 4. Okay, so it becomes 6 over 4 times 1 minus X over 12. Okay, great. So now we have a, what was the name? We have a FCD. Now let's find out, what's the name? Find out FIJ. All right. So summation of forces in the X direction equals 0. So FIJ plus FCD plus FDI cos theta equals 0. All right. So FIJ, we know what FIJ. Okay, so what we need is actually FIJ. So FIJ is equal to minus FCD minus FDI cos theta. So okay, let's see. So we know our FCD. I mean, we can put this whole long equation. So this is 3 over 2. So 3 over 2, 1 minus X over 12. Okay. Then minus our FDI was 5 over 4. 1 minus X over 12. Cos theta is what? 3 over 5. So you can simplify this equation if you want. All right. We'll just look at how simple it is. So again, I'm going to bring my table that I worked on. Just make a copy of it and come and paste it over here. All right. So I'm going to bring my table that I worked on. Just make a copy of it and come and paste it over here. All right. So I'm going to bring my table that I worked on. Just make a copy of it and come and paste it over here. All right. So I'm going to bring my table that I worked on. Just make a copy of it and come and paste it over here. Okay, great. So here, even though we're using the left-hand side for the calculations, it's valid for when the load is between C and G. All right. So let's look at it. So I mean, here you can just put it in your phone, for example. So I'm going to work with the FDI. That's an easier one to work with. So you have 1 minus. So if you what am I looking for? So it becomes what? X over 12. Sorry. So let's see. So if X is 6 meters, uh, no, we've already done with 6, sorry. So it has to be between D, so between D and G, not C and D, sorry. Between D and G, sorry, because it's on the right-hand side. So between D, so D is what? 9, sorry. Because we're done with the C already. So between D and G. So when X is 9, we get for FDI, we get 5 over. I have this thing nicely drawn, and I think I zoomed. I made it bigger than I was supposed to. Just give me a second again. Let me just make it smaller. Making it smaller is nicer. Okay, I think this is the best I can get it to look. So a D is 5 over 16 at E, which is 12 meters. That'll give us 0. Okay. Then at F is 15. So you get minus 5 over 16. Then at G, which is 18, we get minus 5 over 8. Right. So if you do it for what's the name? FCD also, we at 9 we'll get 3 over 8. At E we get 0. Then at G we get minus 3 over 8. And then at F minus 3 over 8. At G we get minus 3 over 4. All right, so let's draw the diagrams. Complete this one. All right, I don't want to take complete it. So you guys should complete this one. Okay. So let's draw our diagrams and see how everything looks like. Where's my ruler to draw the horizontal line? Okay. So again, we have A, B, C, D, E. Okay, so A, B, C, D, E, F, and G. So let's just look at this quickly. Sometimes it's best to leave your answers in decimal, especially if the denominator is not the same, because then it's easier to tell how your curve is looking like. All right, so just take note of that. So let's draw for FDI. So FDI, we have 0 over here. Then so minus 5 over 16 will be what? 0.32. So let's see, it goes down here, 0.313. Then at C, it's supposed to be double, so that means 0.625. So that's at C. Then at D, it comes up here to be 0.313. Then it goes to 0 again. Then it comes to minus 0.313. Then what again? Then it comes up again. All right, to be I'll make sure I'm the same line. Okay. Then it comes up again to 0.625. Okay. So you have this funny shape diagram. All right. So let me just see how best I can draw everything to look nice. It's from the ILD diagrams for statically determinate structures are always straight lines, right? If they are statically indeterminate, then there'll be curves, right? So the best I can have you to look. So I'm trying to get this to look nice. So please, if it's not looking too nice. Okay, so this is how it looks like. It is an interesting diagram. Okay, so let me just get the other points which were a bit off onto the structure. Should have used a different color for the points. Okay. Okay, so this is the diagram for the so this is the ILD for member DI. Okay. So and we can draw something similar for member F's. So we can also draw something similar for ILD for member CD. And then for member CD, very similar. Oops, take this guy away. Okay, let me just be lazy, copy this and bring it down here. And again, with that one, when you draw for CD, it goes all the way up here. It goes through 0 at this point, then it comes back higher. So you should end up with a diagram like that. Okay. Which is 3/4, 3/4. I think yeah. So this is negative, positive, negative, positive, negative. All right. So these are like the steps that you require to solve the ILD for what's the name? For what's the name? Yeah, for a class of this nature. I posted an assignment on this topic on V Campus around the 20th. So that's like last week Tuesday. No, not 20th is when? Was when? Yeah, was last week Saturday. Not last week. 2 weeks. Yeah, 2 weeks. I mean, yeah, Saturday. But for some reason, I did not. Normally, when I post assignment, I hide it so that when the time is up, it will show. And for whatever reason, it did not show until yesterday that I went back to the V campus. And that's when I saw that I had not made the assignment visible, the assignment 6 visible to you guys. And it's due today, right? So because I did not make it visible, yes, I'm now showing it all right, but then it's not going to be an assignment. You can try it on your own. If you have any questions, you can ask, but then I'm not going to grade it. Okay. So let's go through this. If you have any questions on the other topics, let me know. So let's talk about the exams. I always like to talk about that off record.